Okay, folks, let's get going. So this is almost the end of the week, for week 4, and the second presentation on assemblies is going to be today. But let me remind you that when I tried to do this problem, I ran out of time, so did not do it with planes of symmetry. Okay. So I'm going to go quickly through this problem where two planes of symmetry are used in one situation. For example, when the two ends are welded against the two ends. Obviously, everything's symmetric along the perpendicular direction. But uh, if I do only welding of one edge of the cylinder or shaft with one edge of the left bearing, this side is completely free, then this vertical plane towards you is not a plane of symmetry anymore. There's only one, which is along the length of the shaft. Okay, and that's how I did the problem last time, except that I didn't use symmetry. So I'm going to quickly go through that, the creation of the model from the beginning, without any dimensions. Okay, any specific dimension. I just make one dimension visible to myself so that I know what the sizes are. All right, so let's go ahead here, and this is the agenda. First, we're going to do this problem, wrap it up, and then we move on to chapter 15, which is a shrink fit problem, and your homework tomorrow is related to this item. Okay, so let's go ahead here. Automatically, a product file is, of course, activated, so I'm going to insert my first part in it. So insert, new part, in this. I'm going to double click on it. This is going to be the shaft. So let me actually call this thing a shaft. Properties, shaft, and shaft. Okay, one of them is a part name, the other one is the instance name. All right, notice that that's because I gave them the same name, it became shaft parentheses shaft. Okay, so it's instance shaft. So let's make this thing. We are already in part design, so on that vertical plane, I will sketch. Let me do the shaft, which was roughly one inch diameter. Dimensions are not important right now, so yeah. So let me actually make this half an inch. Yeah, half an inch radius or 1 inch diameter. 0.5. Exit. Padded by say 10 inches each way. Let me see how it looks like. If I do 5 inches each way, mirror extend, it's going to look like that. Yeah, why not? We make it like this. Now I did create a stand on top of this because I want to apply the load on that stand. Okay. In the book, the downward load is applied to the entire shaft, which is physically impossible to do. Okay. So on the way I did it on that horizontal plane, I sketched. Okay, so you know what? This time I'm going to make a rectangle. How about that? Instead of making a circular thingy, I'm going to make it like that. Why not? Exit and then pad it. Let's bring it down, 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 down. Okay, that's too much down. So maybe 0.7 maybe. Okay, good. I'm going to put the load on this. Now, somebody asked me the other day, I made it a bit taller, said that, well, shouldn't it be, shorter? Well, I mean, this is just something that I make to put the load on it instead of putting on the whole shaft. The real life is a different story. If you are sitting on that shaft, okay, there's not even a stand there. Okay, so what you need to do, put your load on a particular area, patch, and that you have to create. You need a feature to put your load on it. Okay, you need a feature. This feature can be something like that, or it can be a surface on that shaft that I have created, and you proceed along that line. Okay, so I'll just leave it like this. The emphasis in these things is doing assemblies. It's not how the load is applied. Okay, so that's good. Let's go ahead and create one of the bearings. So insert a new part. Always say no. I always say no. You can read it and see what it actually says. So on that vertical plane, I will sketch. Why don't I project, because I'm lazy, I'm going to project this circle. Automatically, the circle is over here instead of me drawing it and dimensioning it. And now we're going to do the rest of the problem. It's yellow because it's a projection. Good question for the test. It's yellow because you circle the right one. Okay. Something like this, and like that, and this, and that. I want to make sure the symmetric, concentric here. So this circle control that circle because I know that the centers are probably not the same place. You can see that it's a little bit shifted. I want to make it concentric. Yeah, now it's okay. And knowing the diameter of a shaft is 1 inch, you have a fairly good idea what these things are. Exit, pad it. Yeah, that's good. I'll make it the same. Okay. So this is going to be my bearing. So let me right-click Properties Bearing and Bearing. Okay. And save everything. So in File, Save Management, Save As, Desktop, New Folder. Okay, Problem 1. We're going to go there. Propagate Directory. So Propagate Directory basically put everything associated with that problem in that folder. Everything. Okay. Good. Now let's make everything out of steel first of all. So apply material. Everything made out of steel. Say okay. Now, when it comes to the other bearing, I mentioned that you can actually go ahead and do another one of these, just like you did here, under a different part. Or you can copy and paste it. Okay. Or after you save, you can insert an existing component. Let me do that this way today, okay, instead of copying and pasting. So I say insert, not a new part, existing component, you click on it, and it says, where do you want to insert this in this product? And it says, where is it? So I go to the folder that I created, and I saved it immediately before I did this, grab the bearing, and bring it in. So I go, it's problem 1, that's this one. Notice the product is there. The shaft is there. The bearing that I made and saved is there. So I'm going to select the bearing and I'm going to bring an instance of it into the structure. And you'll notice that there is a bearing here, another bearing. Now, the reason you may want to do that is that if you copy paste or if you literally make the parts, these will take there's overhead associated with it. It takes disk space and all these things. This is not creating another part. It says, hey, I have a part that I have saved and I want to use it for some other purpose. In this case, the problem that you see here. Now they're sitting on top of each other. So if you move these things, for example, if I translate in the X direction, you see that there are actually multiple copies, 2 copies, because I created one and inserted a copy of that, and a component, an instance of that, basically. Okay, rest of the problem. First of all, I suggested that you anchor something. Okay, anchor. This is the correct constraints toolbar. There is something that looks like an anchor, and I'm going to anchor the shaft so that when you move things around, this guy stays put. Okay, so for example, this is very easy. I say coincidence between this face and, okay, Okay, that face. Now, when I do this, if I don't pay attention here to these arrows, what happens is you update, you see that it's going to look like this. In other words, I want this thing to be flipped around. Without actually rotating these things and do this kind of a thing, I can actually go to that constraint that I created, flip the arrows, and hopefully they'll take care of it. This arrow, one of them you flip, and you update. It did the right thing, except that just like last time it did rotate there. Yeah, so let me, and the different ways we can fix this. For example, you can say, okay, let me maybe literally rotate this manually about the x-axis so that it's closer to where it was before, what I want. Okay, let's do this one. Coincidence between this, and I'm doing the same thing. Coincidence between the other side and this side, okay, and update. Okay, good. And if you want these things to line up, coincidence between this plane and that plane, and update. Okay, whoops. See, it's tilted. But that's easy. That's easy because what we can do is say angle constraint between this plane and, for example, the bottom plane. And I want this thing to be parallel, right? Parallel. There we are. Look, you've got to make this thing somehow. I don't care how you do it. That's your part. Now, on the test, if there is an assembly problem like this, obviously you have to solve it as an assembly. Second thing is that making a geometry has a few points. Just the homework tomorrow in the lab is actually from last year. It'll give you the breakdown of the marks, how we marked it. First of all, if you did something that didn't run for whatever reason, automatically, whatever number of points that problem has is going to be discounted by 35%. Because at the end of 6 weeks, not 6 years, 6 weeks, you should be able to run it at least. If it's not running, something you're not doing right. Fundamentally, after 6 weeks, you're doing something fundamentally wrong, and you're going to lose 35% automatically on it. The rest of it, even though it didn't run, we look at the rest of the stuff. Did you correctly take symmetry consideration? Did you put the correct restraint? Did you put the okay? Depending on that, we discounted by 35%. You get your marks. Okay, so if you have any question about this marking scheme, talk to me tomorrow. I'm starting your homework. Now, okay, very good, and we have to cut it now. You can go to individual parts and cut them, but you can also do it in the assembly. For example, there is a saw in the assembly right here. Look, notice that I am in the assembly zone right there. There is a saw there. This saw will, what is it? If sometimes you don't get any feedback, just read this. Select FA, a plane or a face, surface, or an existing split. So I want to cut it with, for example, this plane. It says, okay, if you're going to cut it with this plane, then three things are affected. You can see that shaft, bearing, bearing. Do you want all of them to be cut? If the answer is yes, just say yes, all of them. Which side do you want to pick? Doesn't matter. Oh, undo. Let's try to do it differently. So again, I select my plane. Which plane? This plane. Read this thing carefully. What does it say? It says affected parts. Let's take the shaft. Let's take this and take that. Ooh. Undo. Okay. When it comes to this and you don't have the time, and you don't have the time right now, split them one by one. And I wonder why it's happening like this. I'm not sure. Why they're not cut at the same time? They should be, unless I'm overlooking something. Let me try one more time. Parts possibly affected. Okay. All right. You know what I'm gonna do? I'm gonna try to do. How many things do I have here? Let me see for a second. This and that and that. Who knows? I'm not sure why it's not working. So let's do it one at a time. Something is not working, and I can't even close. Oh, okay. Listen, I don't know why it's not cutting it at the same time. So let's go ahead and do it again. Do it again. Question? Comment? Okay, so let's do another one. Do another one mean another part. What can I do? So bearing. Oh no. Where is that assembly? Okay. Let me delete these. Man, I didn't expect to get bogged down here. Okay. Since I have miserably failed in doing what I wanted to show you, what I'm going to do is I'm going to go to parts individually, cut them. I went to the shaft, get the split out. I don't know why it's not working. I don't know. So you want me to go back here? So let's see. So it says select the plane. Okay, so that's this plane. And then it cuts the shaft. You want me to try this bearing? I'm wasting too much time on the test. Okay, you can get to the bottom of this yourself because I failed to do that. Okay, so because these things happen, you either have to bite the bullet and do it a different way, or spend time, hours, or not hours, minutes on it trying to get something done. It's entirely up to you. Okay, so let's try this. This is going to be the shaft. You keep that side, no problem. Go to the other part. Go to the other part. Now here, if I split one, the other one might get split too, which is fine. I don't mind. So split that plane. Yeah, it did it. But look what happened. Okay, then look what happened. Because of the way, remember, probably I rotated these things. Now here you have to decide what you're going to do. You can take this thing and remove the constraint, put it on the other side. Okay, and there's or yeah. So let me do the following. This constraint was for these ends. Okay, let me delete this. I have to go to the assembly to do that. Okay. That is the one disadvantage of doing instances. Okay. Uh, but if you had copied it and you cut the other bearing, it'll ask you which side you want to keep. Happens. Okay, so let me delete this. Let me delete that. Let me delete this. And now we're going to move this. We're going to go to the assembly and move this thing to the right place. So let me see. Rotate about the z-axis like that. Okay. Translate it in the x direction. Ooh, translate in the x direction like this. Let's try to put constraint between this face and that face and pray. That's good. That's good, except that we're not done yet. So coincidence between this axis and that access update. There. Okay? I'm not going to waste any more time on this thing. So, and in fact, I'm not going to do two planes of symmetry. Okay? So, but it is on the video. You can watch it. Okay, so video from last year. Or I may have a better luck, and with the second group, I'll try to record this thing. Yeah. This one, I'm intending to weld only one side. Yes, I'm intending to do only one side. Therefore, it does have one plane. But if I had done welded on both sides, then this vertical, yeah, that's also there. Let's move on. So we go to human builder. We don't want to go there. Katia immediately sees three parts. So it's going to mesh it. It's going to mesh it. So, but you know what we did last time? We made the local mesh refinement around the hole. I think with this group, I made everything small. But with the second group that I posted the video, I actually, around the edge of that stand, I made it smaller. You may want to look at that if you want. With you guys, when we did this problem, I made everything smaller for the shaft. Okay. Okay, good. So let's do the rest of the problem. All right, the bottoms are clamped, and somebody asked me, I think it was in this section, somebody asked about that anchor. Wouldn't that, kind of clamp something? No, that stuff that we did with assembly constraints will not transfer into generative structure analysis. Okay, so you have to do, all these things have to be done. Okay, so let's put a load here. And remember, if you are dealing with a force, then you divide whatever the force is by 2. Okay, so let's pretend that there was 2,000 pounds here. I think last on Tuesday it was 2,000 pounds of the whole thing, or 1,000. Anyway, divided by 2. If it's pressure, leave it the way it is. Okay, so good. Now we need to do connections. Surface sliders. Not here. Under restraint. Surface slider. This is a plane of symmetry. That's a plane of symmetry. This is a plane of symmetry. This is a plane of symmetry. And this is a plane of symmetry. Any one of these missing on the test, that particular component, maybe 3.4 point out of 26, is going to be deducted. No part marks. Okay? So pay attention to what you're doing, please. I know it may not be, you might not consider it to be fair, but there must be a distinction between somebody who doesn't make a mistake and somebody who does, inadvertently or on purpose. All right, so now we create a connection, one on this side, on this face, and then hide this, the inside of the hole as the second component. Good. And do another one between inside of the hole, because it just happens to be available to me on the screen. And the second component is the face of that thing, the face of that shaft. So let's bring this thing in the front. Okay, good. So 2 connections have been created, and that's signified by either looking at the tree, 2 of them, or these red lines will tell you that it was okay. What kind of a connection is this? If you bought this shaft and brought it home and stuck it into there, what would the nature of the connection be? This is saying they're friends and enemies and relatives and things like that. It doesn't say how. Connection simply means there is a relationship between this guy and that guy, this surface and that surface. It doesn't say how. If the problem statement says these are fully bonded, that end that I put in there is fully bonded, fully glued, whatever, then it's going to be faster. Otherwise, it's a contact. It's a contact connection. So you go to contact. I think this is contact. What is it? Second one. So this is a contact. You just cannot penetrate that. And this is a contact. And that's signified by those See this? You see these two things on top of each other, next to each other? It looks like contact. And don't fool around with these. Just to make sure, if you're that confident that you know that what you're doing, then fine. But I didn't say anything about friction coefficient, therefore you should not use it. Okay. For example, that's an example. Now, if we run this thing, it's not going to work because this whole thing slides out. So the problem clearly says take the edge of the shaft and weld it to the edge of the hole. The problem will say that. So what you do is do a third connection. Okay. It's easier if I hit this thing. So the first component is the edge of this shaft, and the second component is the edge of that hole. You got to be very careful here because edge of that hole is that sketch. So you have to hide this and then select that edge. Because if you try to pick it with that sketch there, you won't take it. Simple as that. So bring it there, and this is the third connection. Because they're fully bonded or glued or fully perfectly glued or bonded, welded, you make it fasten. Third one, on here, we say okay. Hopefully we didn't do anything, we didn't forget anything, so we're going to run it. Now, notice that when I opened that window, it didn't give me anything. Usually it says all. So what I did, I used the pull-down menu and selected all. For some reason, it didn't give me that. I don't know. So that's what I'm saying. If you cannot run, possibly because you can't find that thing. You see a blank box there. So I used the pull-down menu, selected all, and then I could pick it. But if you didn't know what to do with that, it won't run. So unfortunately, 35% is down the tube. Now, it doesn't have to be like that, because if you have done your work and you saved it, then you execute, you're back into it. This time, do the analysis, just do everything, put it into place, and run it. Okay, so sometimes, not a big deal. There we are. I'm not going to do any more of this. Okay. Notice that because this side is not welded, as this thing bends, it just slides out. Okay, if both sides are welded, then you need two planes of symmetry. Okay, and then of course half of it you don't even do. All right, any questions? All right, so good. Let's share this. So the second problem that we are doing is right there. We have two different materials, in this case, bronze and steel. The bronze is the inside one, that yellow one. The diameter of that yellow one is a little bit bigger than the diameter of the gray one. So if you try to put that yellow thing in that gray thing, it won't take it because it's a little bit bigger. But I want to insist that this thing ends up in the middle of that gray thingy, middle of that hole. I can take a hammer and just bang it on the brass and force it in, and that's one option, but that may not be a good option for whatever you have in mind. You can damage the brass, you can, stuff like that. So how do you put something that's bigger instead of that thing that's smaller? How do you do that? And if you don't want to force it, do you have any suggestions? Look, I have a brass piece. It's a little bit bigger than this steel piece. And I want to take that brass and put it in that steel piece without banging it and hammering it. I don't know what you mean by that. Okay, hang in there. I give you this brass piece, and I give you the steel piece, and you're in your kitchen, and I say that I want you to put this brass piece inside of that steel piece. That's my question. Yeah, that's it. You eat up the outer ring, it grows, or you put the inner ring in the fridge, in the freezer. It contracts, and then bring it out quickly, stick it in there, and let it go back to where it goes. That's called shrink fit or pressure fit. Yeah, both of these terms are used. I think Katia calls it pressure fitting, but don't get hung up on the name terminology. Okay, so it's one of those problems that actually has an analytical solution, right there. And what do we mean by that? One of the things that you want in this shrink fit problem is know how much force, how much pressure is between the two interface, between at the interface. How much pressure is the steel putting on the brass, and how much pressure is the brass putting on the steel trying to expand it? Okay, that number is extremely important, because if it's too low, and this is, for example, a shaft that's shrink fitted hypothetically inside of the disc. If it's too low, when it turns, it may come off. The moral of the story is that that piece is extremely important. There is an analytical solution for this, but only for the case of this nice little thing. Tomorrow's lecture, tomorrow's homework is going to be 4 holes on the steel disc. This formula is no good anymore. Okay, so all right, that's what we're going to do now. In fact, what you can see is that if you look at this thing shrink fitted, the 3 principal stress directions that are important is along the length of the shaft. That's one of them. The other one is the radial, one pushing on the other one. And the final one is the hoop for both of them. One thing is for sure, that the hoop stress is the critical stress, and it's going to be discontinuous. You can see that this guy is the hoop stress. There is a jump discontinuity at the interface because different material properties. Young's modulus is different. Young's modulus in brass and steel are different. So do not expect the same stress distribution in general at the interface. There's a sudden jump. There's the stress that is continuous is the radial one, because the radial one is pushing on the other one. It's the same stress, except that one is pushing on the other one pushing on this guy. So that dotted one is actually the radial stress. Radial stress is continuous. At the ends, the inside of the brass and the outside of the steel is 0. It goes to 0. In the middle, it's some value and it's continuous. It doesn't matter from which side but hoop stress is discontinuous. You can see that. The axial stress like that, if it's 2 discs that are shrink fitted, the axial stress is 0. Because after all, when you shrink fit, this guy pushes on the other one, nothing restrains these from going up and down, etc. If these are 2 tubes shrink fitted inside of each other, you can take a brass tube, a little bit bigger than the steel tube, put it in the oven, put the other one in the oven, bring it in and stick it in, and then it becomes shrink fitting of a tube inside of a tube. Then there is a stress in the vertical direction. Okay, so what we do in that particular case, we take a slice. We take a slice of this long tube instead of the other long tube. We take a slice, and as long as that slice is not too close to the end, they do behave the same way. They actually don't elongate that way that much. So here's the story. If I have tubes shrink fitting inside of one another, all I need is to take one slice. The top is on roller, the bottom is on roller. This is not because of symmetry, because this whole thing actually is the same unit-wise as you go up the tube, they all behave the same way. If it's 2 discs which are shrink fitted inside of each other, as it was the test last year, midterm last year, which is your homework next tomorrow. It says that thin discs, okay? It doesn't say tubes, long tubes. So don't put any restraint on the top and the bottom anymore. However, there you have a plane of symmetry, okay? So let's look at our own case, not tomorrow's case. Our own, this is the one that I'm doing, okay? Obviously, you can take a middle plane of symmetry, but what difference does it make? It's going to be exactly the same problem. It's just that the thickness has changed. Look, the way it is right now, the top and the bottom, because I'm assuming it's a long tube, they're roller. Okay, you want to take a plane of symmetry? No problem. Take it, and then you're going to put another roller there. So it's the same thing. But if I ask you to take a 30-degree sector, you can do that. 90-degree sector, etc. Be prepared for that. Anyway, any questions here? Move on. All right, so let's start with the product file. Let's do the brass one. How about the inside one? So insert a new part in there. And I'm going to call this thing brass inside. Notice that I did not even bother changing the instance name. It's okay. You can say part one. I don't care. Let's see. It says part one. Fine. Make it. Part design on that plane. I will sketch, and I will take, I don't know, what do you want? 45, 30, 90, it really doesn't matter. Okay, I'll take 35. 30. Okay. So I'll draw, where is the circle? There we are, like so, like so, like so. And another one, same animal, like so, like so. So draw a line from here to here. Draw another line from here to here, and do a cleanup, quick trim. Okay, quick trim. Get rid of this, get rid of that, and that, and that. Okay. Now, hopefully this will go through the origin, and it will go through the origin because when I drew it, I drew the line from the origin all the way up. So it should take that constraint into consideration. Now, let's give some dimensions here. If not, we have to fix it, no problem. So this is the inside radius of that brass piece, which is 2 inches. And this is the outside radius of that brass piece, which is 2.001. 2.001, a little bit bigger, thousandths of an inch bigger than the one that I'm going to make on the outside. Look, oh no, 4.001. Oh, wait a minute. Hang in there. My dimensions are kind of screwed up here. I was looking at the inside diameter of that hole was 2, not 4. So let me clean this up. This guy was supposed to be 1, radius 1. Okay, now this is going to be 2.001. Yep, there we are. Now let's do an angle between this and that. And I'm going to make this thing 45 degrees. I don't know what I said, 30 degrees. Okay, fine. Now notice that when I was making this guy, my constraints were not properly done. So what I can do is I can say this point, control that point. You can make it 0 or you can make him coincident, either way. Coincident? Now this guy's not going to go through that. Yeah. So this, I'm running into all kinds of problems today. This control that, make it coincident. Believe me, that's what I want. That's good. I don't know why I ran into these problems. Okay, exit, pad it, 1 inch. We have taken 1 inch slice of this line pipe instead of that other line pipe. Okay. This is made out of brass, so let's apply material at the part level. You have to do it at the part level because at the assembly it puts it on all the parts. By the way, let me make the color of this yellow for no good reason. Okay, good. Let's go there. Insert our steel piece. Okay, so insert new part. Let me call this thing steel. Right click properties, product. I'm not going to bother with the instance name here. Steel outside. And let's make it. So we go there, double click on that same plane, XY plane. I will sketch. Okay. I'm going to be a little bit more careful to avoid those mistakes that I made that I had to go and fix. So here's what I'm going to do. I will draw, instead of, I'll draw a circle like this. And this is going to be 2 inches, a little bit smaller than 2.001. And another one like this, which is the outside, and that's going to be 5 inches. And I'm going to draw some lines, a line from here to here. We'll do a cleanup in a minute, and another line from here to there. Okay, and let's do a quick trim and get rid of the stuff that we don't want. So quick trim, I don't want this. I don't. Oh no, I do want that. Undo. Control Z. Okay. Oh, that's because this thing was on. Control Z. There. Okay. So quick trim. I don't want this piece. I don't want that piece. I don't want that. I don't want this. And I don't want that. And this thing on the top. Okay. Hopefully everything else is okay. Let's dimension these things. So this one is going to be 5. 5 means 2.5. Diameter 5, radius 2.5. Okay, 2.5. And this guy, radius of this is going to be 2 inches. Look at the front. Yeah. Okay, this angle we want it to be 45 degrees. Notice that I did not run into those problems that I had before because of the way it's done. I'm not suggesting one or the other. All I'm saying is that just do whatever you like. Make sure it's right. Come on. Something weird. So what was this angle? Let's go check that angle. Well, I thought it was 30. I don't know what I put in there, but maybe because of all those changes that I made. Notice that the color, by the way, is not white anymore or green. When you change the color to yellow, this happens. Okay, so let's put an angle constraint between this guy and that guy. Should be 30 degrees. Yeah, it is 30 degrees. Why is it not looking good then? So exit. It was 30 degrees. Where is the other guy? Where's my other sketch? Oh, exit. I don't like it. So is this not going through that anymore again? So let's try. This should go through that. Coincident. It is coincident. You know what? When I look at this view on the top with the yellow one, I don't think it actually goes through the origin. Yeah, one of these lines is not going through the origin. See, just trying to make some shortcuts here. See, this line should go through there. It doesn't look like it. This control that. I'm not sure. Are they coincident? It is coincident. 30 degrees here. 30 degrees there. How could it be? Something is bothering me. It's not working right, and I don't know what it is. Is this thing going through there? Let me check. Is this line going through there? Control this point? No. Yeah. Happens. Okay. Exit. Exit. Pad it by 1 inch. And we make it out of steel. This was such a simple problem. It was simple. It's just that the way I did it, those constraints got discounted. Okay, so metal, make it out of steel. And I want to show you something, by the way. I have a feeling I know why I was losing those constraints. I have a feeling I know why. We'll find out in just a second. That's on this part. Say okay. Let me show you a toolbar here, and you may want to try that. I'm going to reset my toolbars. Okay? Because the thing I want to show you is not there. Okay, and definitely it's not hiding. I must have closed it. So you go Tools, Customize. We're pretty much done here, but I want to show you this. I want to find out why is it that I thought I was doing the right stuff, but it was not actually happening. So let's get the toolbars, restore all contents, restore all positions, and say OK. The toolbar that I want to show you is, I know, actually, let me go to one of these sketches. I think now it is okay. You see, in the sketch, as I draw things, constraints are automatically picked up. For example, if a line is supposed to go through that point, in other words, I drew my line starting from that point like this. So that line should go through this point. If inadvertently you uncheck one of these, which one is it? Dimensional constraint, geometrical constraint, right there. If this is off for some reason, what you think you're doing may not work. So these two icons, these two icons on the right side, sketch tool on the right side, should be activated. Otherwise, even though you may think that something is sitting on a horizontal line, on the x-axis, for example, it will not. These two must be on. Moral of the story, get this thing done, one way or other. Excellent. Now, we go to the analysis. Now, when I go and check my video, I will see whether those icons were on or not, because I have a feeling that they were off, whatever reason. CATIA meshes both of these, okay? And if you want to look at the mesh, right-click Mesh Visualization. There we are, okay? Now, I know that there is a severe discontinuity at the seam. See that at the seam? Seam is this line. I can change the color of these if you want. so that you can see it better. So you go here, right click properties. I don't know, properties. I make the color different. Graphics, color, I'll make it different so that you can actually see orange. There, okay. At that seam, there is a discontinuity in the hoop stress. So you want a finer mesh there. You want a fine mesh at the interface because you know that there is a severe discontinuity there. So local mesh definement, let's do that. So you know how to do it. Right click mesh visualization. Do a local mesh definement. And Katia is going to say, hey, you know, you have two elements. Which one do you want to refine? So I have to go pick this, and then it says where. Okay, so let me just do, although you have to do it on both sides, but I will do it only on one side. On this side, I'll make it, I don't know, 0.08. Okay, let me actually make it smaller. 0.04. Good. Right click, mesh visualization, or activate. Come on. There, you see this? You see this? The orange one? The orange side? You have a finer mesh. I should do it on both sides actually, but I'm not going to do that. Okay, good. So let's go ahead and do the rest of the problem. And the rest of the problem is very straightforward. So as far as the restraint is concerned, all of these are planes of symmetry. So surface slider, where is this stuff? Because I reset my toolbars, they all end up in different places. Where is it? Come on. Oh, it's on this side. Surface slider, help me. Top, top, side, 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 bottom, bottom. Do not put a surface slider on this face or the inside face because you lose the mark for it completely for that particular problem. Now, I have to create a connection between these two. Analysis connection, the usual thing. First component, let me hide this. Second component, let's get the other guy. It's still sitting here, there. And of course, you're just going to see a big dot there. No red lines because, you know, these two centroids sit on top of each other. There's nothing to it. This is the connection. Now, when you go to connection, you have already used contact. You have already used fasten. The third one, the second one from the left, it says shrink fit. Shrink or pressure fit. Pressure fit. You click on it, it says, where is that place where there is possibility of overlapping? It has overlap. It's this connection that I created. Remember I selected those two faces right there? It says, what is the overlap? That's the radial overlaps. One was 2.001, the other one was 2.000. Radial overlap, the amount by which these two pieces have overlapped. That's what you have to plug in right there. Overlap. I put it in because I did this thing last year. 2.001. It was the difference of the small radius and the big radius. Okay? That's it. Run it. This is not a big deal as far as software goes. Essentially, it says that these two faces have to separate by 0.001. It's really a contact problem. What is this? Allow access. Okay. I don't know what this thing is. It's running. Trying to push them. Push them apart so that they mate. Give me 2 minutes and we're done. By the way, the symbol for shrink fit, you can see what it is. Something inside of something else, right up there. Right up there. This is going to run. I just want to show you show you something about the results, and then we're done. This is why on the test we ask you to use minimum, not the minimum, but the linear element default size, unless we ask you to refine. And even then, we're not going to tell you by refining by how much, because I just want to make sure you know how to do it. Okay, so this is, it's going, it's going. Should not take this long. I don't know, something happened that this is not a big problem. It's a Mickey Mouse problem. Okay, but still something is happening on my computer. Unfortunately, when you try to do anything, it says not responding. So if there's a stop and kill button somewhere, but if you do it, still doing its own stuff. For me, if I had to stop this thing, I would do Control Alt Delete. There's no other option, and delete the run. This is why I should have saved, so that at least I can bring it up, maybe make the size smaller or something along that line. See, it's not responding. It's not going to crash, but I'll tell you what. Oh, computing in progress. Okay, so contact computation 76% complete. You can't trust these numbers, anyways. So uh, let me quickly show you what I would have expected to happen. Okay, because otherwise this. Uh, okay, good, finished. All right. First of all, von Mises stress. The reason this is happening is that the scale is magnified, because otherwise you can't see. If you want to see the real thing, set the scale to 1. Set the scale to 1. And there is a reason. It made everything 345 times bigger. So the steel is trying to come in. The steel is being pushed out, but it shows you 345 times bigger. The brass is trying to come in. It's made 345 times bigger. So if you really want to see what's happening as far as the geometry, set the scale of 1. The real thing. There. And if you want to see the displacement, of course, you can change it to material shading. There. This is von Mises stress. And notice that there's a red in the middle because material properties are different. That is the von Mises stress. Von Mises stress uses axial stress, radial stress, hoop stress. Radial stress is continuous, no problem. Axial stress is 0. No, it's not 0, but it's some number because I put several sides on. But the hoop stress is discontinuous. That's why there is a big red dot in the middle. Okay? That's it. So I'm going to post this. It's good to see what can go wrong. So many things went wrong today. I'll post this thing. If you have any questions, I'll be around here. I'll be right with you. Let me stop this thing the right way before I